So in this class, we shall be discussing with metal carbonyl complexes. Now, the discussion will be restricted to exams like entrance exams, like postgraduate exams for, entrance exam for postgraduate courses. Okay. So we shall be discussing in brief. A lot of conceptual discussion will not be there in this class. So first of all, if you look at the metal carbonyl complexes, for the first transition, you'll find that it start with, if you look at neutral carbonyls, you'll find that vanadium hexacarbonyl, chromium hexacarbonyl, then manganese, it forms Mn2CO10, অর্থাৎ the monocarbonyl, that means the mononuclear carbonyl complex is not known. Then iron FeCO5, Fe2CO9. So these complexes, they are known to exist, and even Fe3CO12. Then for cobalt, mononuclear complexes, they are not known. Then CO2, CO8, binuclear, and tetranuclear, CO4, CO12. And for nickel, NiCO4. That means we are actually showing the carbonyls for elements যেমন ধরো স্ক্যান্ডিয়াম, টাইটেনিয়াম, ভ্যানেডিয়াম। এর আগে কি আছে? স্ক্যান্ডিয়াম, তারপর টাইটেনিয়াম, then vanadium. That means this is group 3, 4, this is 5, 6, 7, 8, 9, 10. So we are discussing with the neutral carbonyls of from group 5 to group 10. So the question is why, first question is why neutral carbonyls of scandium and titanium are not known. The reason is very simple. If you look at the number of d electrons, if you look at the number of d electrons in the metal centers for vanadium, দেখো scandium হচ্ছে 21, 22, 23. So you know that according to 3D 4s anomaly, after 18, all the electrons will enter the d orbital. That means it is a d5 system. So this will behave as a d6 system, d7, d8, d9, and d10 system. So carbonyl, see, the stable neutral carbonyl starts from d5. Why is it so? Because carbon monoxide, this is a pi acidic ligand. Carbon monoxide is a pi acidic ligand, isn't it? So if carbon monoxide is a pi acidic ligand, naturally it will stabilize metal ions, stabilize metal centers in lower oxidation state. Pi acidic ligands, it will stabilize metal ions in lower oxidation state, that is having excess d electrons. So if there are excess d electrons, then obviously the oxidation states will be lower. And you can well understand that in all these cases, the oxidation states are zero valence state, isn't it? So from D5 onwards, it is stabilizing the metal centers. But if you look at titanium or scandium, such neutral carbonyls of titanium and scandium, they are not known. Now, if you let us start with this chromium hexacarbonyl. If you look at this chromium hexacarbonyl, you know that as per 18 electron rule, you know that 18 electron rule is applicable almost always for organometallic complexes. Okay. Now, as per 18 electron rule, if you start with CrCO6, see, for CrCO6, CrCO6. If you think in terms of 18 electron group, देखो chromium में how many electrons are there? Chromium is 24, isn't it? So there will be 6 d electrons, 6 outer electrons. 18 plus 6 24. So 6 plus 6 into 2. Each of these carbon monoxide is a 2 electron donor as per 18 electron rule. So there are 18 electrons. So it's a stable complex. Now if you look at Mn, manganese, after chromium comes manganese, and we have mentioned that this mononuclear manganese carbonyl, this is not known to exist. The reason is very simple. If you look at, if you count the total number of outer electrons, see manganese is 25. Manganese A, that means there are 7 outer electrons plus 5 into 2, 10. So this is a 17 electron system. So since this is a 17 electron system, this is unstable. This is unstable and this is not known. This is not known to exist. So what happens, even if it is formed, this will undergo dimerization to form MnCO5, MnCO5. Now, when it undergoes dimerization, 2 more electrons are incorporated. That means each manganese center gets an additional electron. So that is why the 18 electron rule is satisfied. Now, even if you just calculate the 18 electron by using the, if you calculate the total number of outer electrons by using the formula, see for 2 manganese, 2 into how many electrons? For manganese, 7 electrons, 14, plus there are 10 carbon monoxide, so 2 into 10, so it's 20, and there is a manganese bond which will account for 2 more electrons. So this becomes 36 for 2 manganese centers. So this is 18 per manganese center. So the 18 electron will be satisfied. Okay. So that is why manganese MnCO5 is not known, but it can readily undergo dimerization. Even during the synthesis, if you add an alkali metal, for example, if this is treated with sodium, metallic sodium, what happens? Sodium, if this is treated with metallic sodium, see, sodium can readily lose an electron, and that electron can be accepted. So sodium can readily lose an electron, and that electron can be accepted by MnCO5. So this will be converted to MnCO5 minus. This will be converted to MnCO5 minus. Now see, this will satisfy the 18 electron rule because there is an additional electron. So MnCO5 minus, this is stable. This is stable. Okay, MnCO5 minus, this is stable. That means we can synthesize molecules like MnCO5. This is stable. Okay, and these anions, they are known as carbonylate anion. Carbonylate anion. Okay. Now, if you look at the structure of CrCO6, see, this is octahedral, perfectly octahedral, no issues. Now, this is এটা হচ্ছে D কত সিস্টেম হচ্ছে D5 low spin. It will not be perfectly octahedral, but it is octahedral. Fine. So দেখো এটা কেন বললাম, দিস ইজ ক্রোমিয়াম। আমরা কি দেখেছি, ক্রোমিয়াম হচ্ছে D6, হ্যাঁ পারফেক্টলি octahedral হয়। ক্রোমিয়াম হচ্ছে D6 low spin. So D6 low spin octahedral. That means, you see, this is the situation. T2G আর EG, T2G EG. The electronic configuration will be like this. So there is no ground state degeneracy. So as per Jahn-Teller theorem, it will be perfectly octahedral. But if you look at Mn2CO10, if you look at the structure of Mn2CO10, see Mn2CO10, the structure is like this. So the geometry around each manganese center is octahedral. Look carefully. The geometry around each manganese center, it is octahedral. বুঝতে পারছো? And you'll find that this Mn distance, this distance is much longer. Why? Obviously, you see, with respect to this manganese, if you look at this manganese, with respect to this manganese, there is a very large group. So there will be steric repulsion. And in order to avoid the steric repulsion, Mn bond distance, this will become longer. But the question is why it will not dissociate. If it becomes longer, there is a possibility that it can dissociate. But still, this compound, but this complex, this binuclear complex, it is known to exist. এই কমপ্লেক্সটাতে এক্সিস্ট করে। তার কারণ হচ্ছে, দেখো, if you look at manganese, this is a D7 low spin system. See, carbonyl complexes will always be low spin because carbon monoxide is a pi acidic ligand, strong field ligand. তাহলে এই যে D7 low spin হচ্ছে, তুমি ভালো করে লক্ষ্য করো, দেখো D7 low spin in octahedral geometry is T2G EG, D7 low spin. So this is D7 low spin configuration. So it has twofold ground state degeneracy. So naturally it will be subject to extensive JT effect. Since it has twofold ground state degeneracy, there will be extensive Jahn-Teller distortion, and that accounts for the longer, and this is why the Mn distance is longer Mn bond. This accounts for the longer Mn bond. Okay. Now if you consider the see, we have discussed about these two. Now let us come to the carbonyls of group 8. Group 8 carbonyls, that means iron carbonyls. Okay, we are discussing about the first transition only. So let us consider this FeCO5. Now this FeCO5, it has a TBP structure. See, you need to know these structures. কারণ তোমাকে যদি এমসিকিউ কোয়েশ্চেন্স দেখো স্ট্রাকচার গুলো তোমাকে জানতে হবে। যদি একটা এরকম এমসিকিউ দিয়ে দেয় যে হোয়াট ইজ দ্য স্ট্রাকচার অফ FeCO5, which of the following is correct with respect to FeCO5? Okay, so one of them they can give you the structure is TBP, so this is correct. So this has TBP structure and you can calculate the total number of electrons. দেখো আয়রন হচ্ছে 26, তাহলে 18 plus 8 26 plus 5 into 2 10, so it satisfies the 18 electron rule. Then next we will discuss about Fe2CO9. See, Fe2CO9, once again, if you think in terms of 18 electron rule, দেখো আয়রনের হচ্ছে 8টা outer electrons for iron, 8 into 2 for 2 iron centers, 8 into 2 16, for 9 carbon monoxide, 9 into 2 18, and for iron bond এই 2 হচ্ছে, so this is 36 per 2 iron centers, so this is 18 per iron center, so 18 electron rule is satisfied. And if you look at the structure, see, if you look at the structure, there there are two bridging carbonyls. Sorry, there will be three bridging carbonyls. So there will be three bridging carbonyls, and at each of the metal centers there will be three terminal carbonyls. At each of the metal centers, there will be three terminal carbonyls, and this will be associated with a metal-metal bond. So this is the structure of Fe2CO9. Okay, so that means there are terminal carbonyls as well as bridging carbonyls. Both are present here. Okay. Then if you look at Fe3CO12, there are two types of structures. I am not going into the structure of Fe3CO12 because that will not be required for your MCQ exams. Now let us come to the group. Let us come to the complexes of cobalt. That means group 9. Complexes of cobalt. Carbonyl complexes of cobalt. So CO2, দেখো CO2 CO8 বলেছি আমরা, তাহলে আমরা এই mononuclear CO4, this is not known to exist, not known, তাই তো? So this mononuclear CO4 is not known. So why is it so? See, if you count the outer electrons, cobalt কত? cobalt হচ্ছে 27, 29, sorry 27, so 18 plus 9, so it's a D9 system. 18 পর all the electrons enter the d orbital as per 3d 4s anomaly. So there are 9 outer electrons plus 4 into 2, so it's a 17 electron system. That is why it is not stable. It is a 17 electron system. That is why it is not stable. Okay, so uh, so in order to gain stabilization, what can happen? There are two possibilities. First of all, uh, if treated with an alkali metal that can readily lose electron, it may be converted to the corresponding CO4 minus. Okay, or it may undergo dimerization via the formation of metal-metal bond. See, it can undergo dimerization via the formation of metal-metal bond. So is it clear? Now if you look at the structure, so if you look at the structure of CO2COH, it exists in two isomeric forms. So this is important. One, as we have mentioned by simple, there is a metal-metal bond and the geometry around each cobalt is TBP. Therefore, around each cobalt center, the geometry around each cobalt center is TBP. Therefore, trigonal bipyramidal হচ্ছে around each cobalt center. And there is another isomer where you'll find that there will be bridging carbonyls. Okay, there will be bridging carbonyls. দেখো এইরকম দুটো ব্রিজিং কার্বনিল হচ্ছে আর টোটাল বাকি কটা পড়ে আছে ছটা সো অ্যারাউন্ড ইচ কোবাল্ট there will be three carbonyls around each cobalt there will be three এইরকম তিনটে কার্বনিল হচ্ছে and there will be a metal bond. So these are the two isomers and we will discuss that they may be distinguished by IR spectroscopy. So we will come to this. See, regarding the structure of CO4, CO12, we are not discussing it. And finally, NiCO4, nickel tetracarbonyl. See, this is a nickel. দেখো নিকেল হচ্ছে কত 28 তাহলে 18 এর পর 10টা ইলেকট্রন all the electrons will enter the d orbital so there are 10 electrons which will be present in the d orbital so it's a d10 system. Now you know that for d10 system there is no crystal field stabilization, isn't it? So since there is no crystal field stabilization and since the coordination number is 4, it will assume tetrahedral geometry in order to minimize steric repulsion. তাহলে এখানে তো কোনো crystal field stabilization নেই. Naturally, steric factor will play the predominant role. So steric factor will guide the geometry. So this will also satisfy the 18 electron rule. Okay. So these are some of the important carbonyls that are known to exist. Now, if you look at the chart shown in the first page, see we started with chromium hexacarbonyl. Now what about vanadium? See, if you look at vanadium hexacarbonyl, VCO6, Will it satisfy the 18 electron rule? See, for vanadium কত হচ্ছে? Scandium, titanium, vanadium মানে 23. 18 plus 5, so it's a D5 system. 18 plus 5, 23. So it's a D5 system, isn't it? So if you count the electrons, 5 plus 6 into 2, so this is a 17 electron system. So in spite of that, being a 17 electron system, it is stable, still stable. ঠিক আছে? It will not readily undergo dimerization. Why? Because see, if it undergoes dimerization, suppose if we assume that it undergoes dimerization, then what's going to happen? This will be converted to V2CO12, isn't it? And what should be the structure? See, there has to be a metal-metal bond. See, if it undergoes dimerization, we should expect that the dimerization should occur by formation of a metal-metal bond, so that each vanadium gains an additional electron. তাতে ওর এই 17 থেকে 1 যোগ করলে it will become 18 electron system, isn't it? And the geometry, there will be how many carbonyls? 6. 1 2 3 4 5. So there will be 6 carbonyls. Now, can you follow this? If there are 6 carbonyls, so there has to be some amount of steric repulsion. So due to steric repulsion, this dimer will not be stabilized. So that is why this reaction will not occur. So because the dimer is not stable. In fact, this is stable up to 70 degrees Celsius. But when treated with suitable metals, maybe sodium, when treated with sodium, it can readily accept an electron from sodium and will be converted to VCO6 minus. So this will satisfy the 18 electron rule. That means dimerization is not possible. That's okay. But it will always have a tendency to assume the 18 electron configuration. So if given an opportunity, it can readily accept an electron to be converted to VCO6 minus. Okay? Now, with this basic idea about the carbonyls, what type of carbonyls, particularly the first transition, we are not discussing about the carbonyls of second and third transition at this level, because we are restricting our discussion to postgraduate entrance exams. So next we shall move to the preparation, the synthesis. See, synthesis of metal carbonyls. Synthesis of metal carbonyls. So first we shall be discussing about reductive carbonylation reaction. Reductive carbonylation. For example, if vanadium trichloride, see, if vanadium trichloride, it is treated with metallic sodium, okay, in presence of diglyme. Diglyme is a ether, in presence of carbon monoxide. So we are adding carbon monoxide. And it has to be carried out at high pressure, 300 bar. So we are treating VCl3 with carbon monoxide in presence of sodium. So what happens? This is converted to, see, vanadium, this is in the zero valence state, okay? And then this sodium, this can transfer electron, can provide electron, it itself being converted to Na plus. That means the sodium is behaving as the reductant. It is behaving as the reductant. Okay. So since it is behaving as a reductant, so vanadium from the zero valence state, it will be reduced. And carbon monoxide, this is the ligand. This will get linked to vanadium. See, initially vanadium is in +3 oxidation state, isn't it? Initially vanadium is in +3 oxidation state, and under this condition carbon monoxide, see, this is a pi acidic ligand, so it requires excess d electron. So when it is in +3 oxidation state, see, vanadium, scandium, titanium, vanadium, তাই তো? তার মানে হচ্ছে it is a D5 system. So with this, sorry, D5 system vanadium, এবার vanadium 3 হলে it becomes a D2 system. So with this D2 system, carbon monoxide cannot form complex because carbon monoxide is a pi acidic ligand and it will require excess d electron. That is why this metallic sodium is required to reduce vanadium center. Okay, so what happens? This vanadium center is reduced and this is converted to VCO6 minus. Once it is reduced, দেখো vanadium এর oxidation state এখন কি হয়ে যাচ্ছে? -1. তাই না? Once it is reduced, now this becomes a D6 system. D6 and it becomes low spin. তাহলে বুঝতে পারছো, it is supplying 4 electrons. This sodium is supplying 4 electrons. তাতে কি হচ্ছে, ভ্যানাডিয়ামটা +3 থেকে -1 স্টেটে চলে আসছে, isn't it? And এর সঙ্গে এটা Na+ যেটা তৈরি হচ্ছে, ডাইগ্লাইমের সঙ্গে Na+ টা একটা কমপ্লেক্স করছে. So this complex is formed. সোডিয়ামটা দেখো Na+ তো তৈরি হচ্ছে, তার মানে 4টে সোডিয়াম, it is providing 4 electrons. 4টে সোডিয়াম একটা একটা করে ইলেকট্রন দিচ্ছে. So this is formed. So this is actually what we say is reductive carbonylation. Reduction of metal center, followed by addition of the pi acidic carbon monoxide, followed by addition of the pi acidic CO ligand. So this is reductive carbonylation. And finally, upon treatment with H3PO4, this is converted to VCO6, vanadium hexacarbonyl. So this is a very famous reaction in reductive carbonylation. Vanadium trichloride being converted to vanadium hexacarbonyl. VCl3 থেকে দেখো VCO6 হচ্ছে, ঠিক আছে? Let us consider another example of this reductive carbonylation reaction. দেখো, if you look at say cobalt carbonate, CoCO3, cobalt 2, cobalt carbonate. Now when this is treated with hydrogen, hydrogen is behaving as a reducing agent. This is the reductant. It can reduce cobalt 2 in presence of carbon monoxide. Carbon monoxide নিচ্ছি আমরা. at high pressure, so you don't need to remember the pressure, মানে carbon monoxide যে pressure নিচ্ছ, and 130 degrees Celsius. So this will be converted to CO2 CO8 CO2 CO8. That means once again, therefore this is converted to the zero valence state with addition of carbon monoxide. So this is reduction followed by carbonylation. So this is reductive carbonylation reaction. Now দেখো reduction হচ্ছে along with carbonylation. Followed? If you look at another reaction, say CrCl3, chromium trichloride. If you remember, chromium 3, it is a D3 system, isn't it? Chromium 3 is a D3 system. Now, D3 system hole, D3 system hole from crystal field theory, we have explained that it is kinetically inert. It is kinetically inert. So reaction with CCl3 is difficult. It will require high temperature, pressure, etc. So in this case also, if you treat this with lithium aluminum hydride, so this is behaving as the reduction of it. Karon we have to reduce this in order to form carbonyl complex. আমাকে ফার্স্টে কি করতে হবে? We have to reduce this. So reduction followed by carbonylation. So this is behaving as the reducing agent and it will reduce chromium to the zero valence state and this is converted to CrCO6. So this is once again reductive carbonylation. Okay. Another example. Say, achha, this is good enough. So we have discussed about reductive carbonylation reaction. Now there are other reactions, for example, direct combination. Direct combination. For example, this is a very famous reaction. Nickel plus carbon monoxide at room temperature and normal pressure, atmospheric pressure. This is converted to NiCO4. Okay. See, directly it is converted to NiCO4 to direct combination. Probably you know that in Mond's process of purification of nickel, what is done is, see this impure nickel, if this nickel is impure, this impure nickel upon treatment with carbon monoxide, very simple, see it will react at room temperature and pressure, atmospheric pressure. So this is at first converted to nickel tetracarbonyl and then upon heating it will lose carbon monoxide and will be converted to pure nickel. So this is a method of purification because if there are other impurities along with this nickel, those impurities will not react. Those impurities will not react with carbon monoxide. So once this complex is formed, if you heat it, then you will end up with pure nickel. Okay. So these are some of the methods of synthesis. Even if you look at another method, say that is starting from mononuclear, if you want to synthesize dinuclear species. For example, if you start with FeCO5, okay, FeCO5, and if you treat this with UV light, it has been observed that photochemical transformation occurs, converted to Fe2CO9. তাহলে দেখো photochemical dimerization হচ্ছে. Okay. So After this, we shall be discussing with the a few aspects of bonding that will be required. ওই বন্ডিং গুলো, if you know the bonding aspects, how the bonds are formed, then only we can move on to the IR spectra of the metal carbonyl complexes. So that will be discussed in the next meeting.